All right, you guys, we're going to start earthquakes, and this is in two parts. This is part one, and it would be best if you did your virtual earthquake homework first. It's really not that hard as long as you have a good computer connection and your eyesight's okay. It should be pretty straightforward to get that done, and it will, answer a lot of questions and really help you. You'll actually be a seismologist and manipulate the data and stuff like that. So I really like it. It's meant for very smart middle school students, so it really should not be a lot of work on your part. Now, we're going to talk a lot about bad things that earthquakes do, but I wanted to start off with a picture from the 1925 earthquake in Santa Barbara. Yeah, it killed people, and that's always the worst thing about earthquakes. But you guys, I was born and raised in Santa Barbara, and Santa Barbara is beautiful. There's lots of pictures of Santa Barbara. The city is really lovely. It's in the Spanish style, and this is the Mission. And after the 1925 earthquake, they looked at what buildings actually stood up. And the Spanish-style architecture buildings, obviously it didn't totally withstand the earthquake, but they seem to have, withstood it better than some of the really cheap and flimsy buildings that were all over what is now downtown Santa Barbara. They all were flattened. And so, when they were going to rebuild Santa Barbara, people got together and made an architectural review board, and they decided that they were going to build it all in the Spanish architecture. Now, it's made Santa Barbara beautiful, but it's also made it kind of expensive and a tourist trap during the tourist season. But it's still beautiful, and I love to see pictures of downtown Santa Barbara with the stucco and the red tile roofs. All right, so here's the information about the homework assignment. You guys, this is fun. This is easy. Do this with your kids, right? You're burned out studying for the exam. Go ahead and redo this. So you have a couple of choices of different places you can make an earthquake. And it's just really, really good experience for you. All right, what is an earthquake? If you guys were playing charades and you picked up the earthquake card, that's a pretty easy one. Somebody might say, oh, you're having a seizure, but usually if they figured out that's not correct, the second thing is, oh, you're feeling an earthquake. So I think everybody, if you haven't at least felt an earthquake, you've seen lots of video of things shaking in an earthquake. Now, the shaking is the release of energy, and the release of energy is caused by movement on a fault. Okay, and faults are breaks in the Earth's crust where motion occurs. And we're going to look at that pretty closely about the definition of a fault. Now, I'm going to need to make sure I point out some different parts of the fault. Now, on a fault, you typically have a line that goes down into the earth, and the focus is the place on the fault where the earthquake motion first began. Now, everybody knows about epicenter. You hear that on the news, and if you are a geocacher, you might actually have famous epicenters from famous earthquakes. The epicenter is the point on the Earth's surface directly above the focus. Okay, so we'll see a slide on this pretty soon. And it's kind of important to know the difference between these because certain waves move out from the focus and certain earthquake waves move out from the epicenter. Okay, we've talked about the theory of plate tectonics, and something like more than 95% of all earthquakes happen on those plate boundaries. If plates are pulling apart, you got earthquakes. If plates are crashing into each other, you've got earthquakes. And if plates are sliding by each other, you also have earthquakes. All right, here's a picture of a fault, and on the left-hand side, we have what's called a horizontal offset fault. And on the right-hand side, we have what's called a vertical offset fault. Now, these pictures are pretty good for us to use because on the left-hand side, we've got the strike-slip fault that's very similar to the San Andreas fault. Okay, it could affect us. And on the right-hand side, this is called a reverse fault. It's a compressional fault. The arrows come together, and so we've got vertical offset, and this is the type of fault that we have up in the city of Auburn and the surrounding areas. Okay, so the definition of a fault is a break in the rock across which motion occurs. You gotta have that offset. If you don't have that offset, it's just a crack or a joint. It's not a fault. All right, now you guys are going to really want to watch my fault type movie. And what I do in there is I use blocks and I just, briefly tell you guys how to understand, the different parts of a fault, the hanging wall block and the footwall block. And you're going to be asked to label these, so you must understand them. Plus, part of understanding the different types of faults is knowing which block moved relative to the other block. Did the hanging wall block go up? Did the hanging wall block go down? Type thing. So you need to know that, especially when we're talking about the vertical offset faults. All right, now really quick here, you guys. Here is a dike. A dike is a igneous intrusion, and a lot of times they will go right up fault lines. And what you have is a miner, and he's probably looking for gold or something. Now the footwall block is where his feet are, and the hanging wall block hangs over the fault, but it's also where he's hanging his lantern. Now I give you a little bit more interesting, at least to me, story about hanging wall block and footwall block and how I remember it in that video. Okay, remember, if you can't see the video in the folder, I've posted it to YouTube. All right, now the first type of fault that we talk about is a normal fault. And a normal fault is what happens in extension or divergence, where the plates are pulling apart. When you take those block models, remember the hanging wall block dropped relative to the footwall block. Okay, this is what we're going to see at mid-ocean ridges. This is what we're going to see in the basin and range. This is what we're going to see at the Great African Rift Valley. Places where plates are pulling apart. Now your book calls it tensional forces. I don't like that name. I like extensional forces. The land stretches or extends. All right, in this case, the force is divergence or extension, and look at the hanging wall block. It has dropped relative to the footwall block. We have some continuous rock units there, and let's say you were on the left-hand side mapping that bottommost layer. You get to the edge and go, hey, where did it go? You look up, not there. You look left, nope. Look right, nope. Look down. Oh, there it is. It's been offset down. Okay, so it's going to be the bottommost layer on the right-hand side. Now what you do is you figure out the geometry. Look at the hanging wall block. The hanging wall block hangs over the fault. The hanging wall block has dropped relative to the footwall block. This is a normal fault, and the stress is extension, pulling apart. All right, here's a really bad shot from back in the early 80s of somebody wearing too short of shorts. And what we have there is normal faults. Now, you guys, once you start recognizing these things, it's great because road cuts have a lot of faults in them. And as soon as you start moving to the east of the Sierra Crest, you are going to see this type of faults. Now, the guy has his hand on a very dark unit there, dark little rock unit. And if you look, it abruptly stops. You look up, I don't see it. Look down, there it is. The hanging wall block has dropped relative to the footwall block. This is a normal fault. All right, now the basin and range is the geomorphological province just to the east of the Sierra province where Rockland is located. And it is an extensional area. If you were to drive from the Sierra Crest to Salt Lake City 15 million years ago, it would be half the distance. It has doubled in width in 15 million years. So it's an extensional area. And if you look, these are kind of fancier looking normal faults, but check it out. The hanging wall block drops relative to the footwall block. And again, the basin and range, you'd be like, well, why is it called the basin and range? Look, you end up with a series of ranges with basins in between. And the German word, a Horst, is a range, and a Graben is a basin. And Graben means grave, and Horst means ghosts, and ghosts jump up out of the grave. Kind of fun. I like German. All right, reverse fault. In the video, you see me take those blocks and push them together. When you have the big arrows coming together, or a compressional or convergent force, you are shortening and thickening the crust, and the hanging wall block climbs right up the face of the footwall block, and we call these reverse faults. Okay, and the American River, the North Fork of the American River, the canyon there in Auburn, you've got a series of these faults. You guys, if you find a Placer County map and you see the faults labeled, that area of Auburn that I was just mentioning has a number of these types of faults. All right, now the last type of fault I want to talk about is the horizontal fault, or a fault like the San Andreas fault, where the offset is horizontal. So we're going to change our view and not look at the cross section for the vertical offset, but now look at the bird's eye view or the aerial view. It's called, again, they got a lot of names: strike slip, horizontal, lateral, transform faults, and we've got a huge one, the San Andreas Fault. The San Andreas Fault is the western boundary of the North American plate. On the other side of the San Andreas Fault in our area, or in the Bay Area, is the Pacific Plate. Now, I have actually flown in a plane and used the San Andreas Fault as a landmarker. Just like a lot of times when you fly in a small plane, you follow, Highway 5 or Highway 80 or something like that. The San Andreas Fault is really, really clear and easy to follow, and it does appear linear from the sky. And in the case of the San Andreas Fault, my transform boundary is a plate boundary where the two plates are sliding by each other. So arrows sliding by each other. All right, in this case, you guys, these type of faults are either right-handed or left-handed, and make sure you watch that video and understand. Now look at this fault. Is it right-handed or left-handed? Picture yourself standing on one side of the fault, look across, and look for your offset feature. Is it offset to the right or is it offset to the left? Okay, make a guess. Now, I hope you had enough time to guess. This is a right lateral strike slip fault. Doesn't matter what side you stand on. Stand and where the stream, all of a sudden it's taken a jog, and it takes a jog to the right. All right, so make sure you watch that video, okay? I put them up there for you, I don't get paid extra to do it. I come in on Sundays when it's quiet and I make those, and they're not beautiful. I don't claim that they are. They're made with a cell phone video camera, so they work though, you guys. They're meant to support you. All right, now don't worry about this. I'm not going to ask you a question, but this often comes up. And no, we cannot predict earthquakes. And for a little while, we were kind of hopeful, thinking, hey, maybe foreshocks, little earthquakes that happened before the main event might help us. And they still might help us a little bit, but I'm not really very confident that we will ever really be able to predict earthquakes. Now, you have your main event, and then you can actually have aftershocks for up to a year after the main event, and that doesn't probably make those poor Japanese people feel very good after last week's big earthquake. Okay, because they've had major aftershocks, including magnitude 7 earthquakes, and they are weaker. It's better than a 9, but man, it's not very pleasant. So again, this is a little bit more complex. In a more advanced class, we might talk a little bit more about it, but it's what it is. All right, now you guys, pretty fun and easy is the mechanism for how earthquakes work. And this was first explained by Dr. Reed, a Caltech seismologist. And he, Caltech is in Pasadena, and he was an expert on Southern California type earthquakes. Southern California type earthquakes are dominated by San Andreas Fault type earthquakes. If you remember from the plate tectonics section that we talked about, when plates slide past each other, yeah, we get earthquakes. But they're shallow earthquakes, and that will come to play later. Okay, now I've got a slide, you guys, and usually I do a little demonstration for my students in class, and I take a meter stick and I start to bend it. And some of those meter sticks bend really far, and then I release it, and it goes back to being perfectly straight. But once in a while, I don't release it soon enough, and I bend it too far and it snaps. Now, the ground can be deformed due to this stress, the stress of the two plates sliding by each other, only up to a certain amount. And then it reaches its limit. And when it reaches its limit, it snaps. And that is a large earthquake on the San Andreas Fault. Okay, then it actually goes back to being undeformed. I had one meter stick in a U practically. It looked like a horseshoe. And then it snapped, okay? And then I had two very straight pieces, but yeah, they were offset. And when it snaps, that is the energy release, and then the vibrations or the shaking that we talked about in the beginning of this lecture is the energy being transferred along the earth. All right, so let's look at the right really fast because it's the easiest. You take the meter stick, you start to deform it. Now, if in B I release the energy, I release the stress, that would go back to being exactly how it was before, perfectly straight. But typically, when you have plate boundaries and plate motions, you don't release the stress. So if you keep doing it, it's going to snap. And the snap itself is the breaking of rocks, and that's the earthquake. And then look at the pieces, you guys. They're not curved. They're straight, but they're offset. Let's go to the left. Here is some land, and we're going to put that stress on it. This is that right lateral strike slip motion. And the land deforms, and we know this because of land surveys. We can measure this deformation. Eventually, it reaches its limit, and sometimes when this snap occurs, it can move the earth 20 feet. That's a big earthquake on the San Andreas Fault. Okay, and then what you end up with is non-deformed but offset land, and then the stress will just keep going, and it will, work its way back up, and then eventually snap again. Now, sometimes the San Andreas Fault snaps big time, 1906, what's called the San Francisco earthquake, but its epicenter was actually Tamales Bay up by Point Reyes. And, this was a big city with some poorly built structures and some bad land to build on, and so it shook down all the unreinforced buildings. Now, the earthquake didn't spark the fire, but it broke gas lines and knocked over lanterns and things, and the fire is kind of more what this earthquake is famous for, really, than the earthquake itself. Now, if you were up in Point Reyes area at this time, the land moved about 17 feet. The epicenter was underneath Tamales Bay. It made tsunamis, smaller tsunamis than we've been experiencing with the footage from Japan, but it knocked out some of those low-lying islands out in Tamales Bay. So, all around kind of bad, but nobody in Point Reyes, I don't believe, died. I think a train fell over, but nobody, got squished or anything, but a lot of people died here in San Francisco. And we'll talk a little bit more about that. All right, here's from that same 1906 earthquake. Now, you guys, if you own a house and you have a fence put in, I think that was a shock. It's so expensive to have a fence put in. So there you are. You put this fence in, and you didn't realize it was put across a fault. And then you go out and you look at it, a couple weeks later, years later, and you're like, hey, who's the drunken fool who put my fence in? Okay, no, you built it across a fault. Now, if you guys see fences like this, it could be a fault or it could be a mass wasting event, the thing that we're going to talk about next, but boy, that would kind of signal to me that, hey, maybe I don't want to buy this property. All right, the land is deformed. You are seeing it, and the features are showing you the road and the fence. Okay, eventually we reach its limit. I have my limit. I snap if I can't take any more, and so does the ground. And it reaches its limit. It snaps. Now it's undeformed, but it is offset. And look at that fence. That is near Point Reyes area. I think it's Olima, and that's a pretty offset fence. It was not offset before the earthquake. All right, now what you guys should grab is there's actually a handout about the San Andreas Fault, and somewhere I wrote down its name, The Seismic Map of California. It's in your weekly folder. And check out the San Andreas Fault. It really does unzipper, California. I grew up on the Pacific Plate. In Rockland, we live on the North American Plate. Okay, and you all probably live on the North American Plate unless you live on the other side west of the San Andreas Fault. It runs, quite the length of California from the Salton Sea out to off Mendocino coast. We talked before about it does connect offset spreading ridges, and it was formed about 28 million years ago when the North American continent ran over the East Pacific Rise. Okay, the Pacific Ocean didn't like like that too much. We ran over its birthplace. And so its revenge in a way is pulling parts of the North American continent off onto the plate, and it continues. It gets longer all the time, and it also moves inland over time. All right, different parts of the San Andreas Fault actually behave very differently. You guys look in the part of Southern California where you see the San Andreas Fault, and notice the thing called the Salton Sea. Okay, the Salton Sea is sort of man-made. The trough, the area, the low-lying area where it was formed, is formed because that part of the San Andreas Fault is actually sliding by each other and pulling apart. Now, you guys, also one thing is you're going to see what we call it's a fault zone, the San Andreas Fault Zone. You see the main strand of the fault, which is in the darkest, line, but you see a whole lot of parallel faults, and some of them are named other things. But if you have parallel faults, they're called en-echelon faults, and they're part of the San Andreas Fault system. Okay, now LA is in what we call a constricting bend, kind of the worst place to build a big city. And that's a place where you're sliding by but also converging or crashing into each other. And the problem with this is that you save up a whole lot of stress, and so if you're only braking every 100 years or so, you are braking big time, and you might have 20 feet of offset. You guys, 20 feet of offset under the city of LA would be catastrophic. Okay, now certain parts up by Hollister, California, okay, I hope you know where Hollister is, you can probably find it on there, is a part of the San Andreas Fault system where it actually creeps by each other. It's moving that an inch a year. There is no saving up, and so you don't really have to worry about the big one in Hollister. I guess if it did break big time in San Francisco, you'd feel it. But every year the sidewalk and the roads and your house maybe even are offset slightly, and so it can be dangerous and costly if you ride bikes or something like that. Okay, now California's not going to fall off into the ocean because we're continental crust. We're too buoyant, but we could actually unzipper, sort of like the Baja California Peninsula has unzippered. So that could kind of continue, and if everything kind of moves the way it is, in 30 million years, Los Angeles might be right up next to San Francisco. All right, now this is a real famous place right here. It's called the Carrizo Plain. It's just east of San Luis Obispo. You guys can find it on that map you were just looking at. And this is the part where I've flown over here in a small plane, and the line is so straight. You can totally follow it. And what we have is on the left, the North American plate, on the right, the Pacific plate. The arrows show you the relative motions. And you've got what's called Wallace Creek. Okay, Dr. Wallace was a very famous geologist, and so this is named after him. And if you guys kind of turn your body so that you're kind of looking from the left-hand side to the right-hand side, and you're pretending like you're flowing down the creek, and the creek would flow from left to right. Check it out. You're flowing, and you take this really sharp right, and then you turn again and go back straight, and that's because that's right along the San Andreas Fault. Now, that is about 500 feet, that offset where it's labeled, and that took about 4,000 years. Now, you guys, the Pacific Plate is moving pretty quickly, and if there was any place I could be, if I knew the big one was coming, I would sit right across where it says offset. I would sit on the Pacific Plate, because when the big one happens, the Pacific Plate will lurch to the bottom, which would be to the northwest, and it will lurch maybe up to 20 feet. So I'll probably fall on my butt, but you notice there's no buildings or trees or anything to crush me, so I'll be fine. Okay, so pretty cool place. I used to take field trips down here. All right, now here we are standing on the North American plate looking at Wallace Creek, and straight ahead we've got kind of a hazy day on the Carrizo Plain, a really cool place. It's a state park now. Or it's a national park now. And you can see that that stream takes a sharp right. And why it does that is that when the fault, or when the two plates slide past each other, it crushes rock. And crushed rock is easy for the stream to erode. So the stream takes that quick right, and then it continues downhill. And here you can really feel that, the North American plate on the right where we're standing, going off to the left to the Pacific plate, that that's the downhill motion. And so it's, going along that way. Now, it gets a little complicated. I think I'll kind of spare you guys some of this offset feature stuff. All right, now seismograph. If you have ever been in Sewell Hall on the Rockland campus, we have a very bad seismograph. But I'm okay with it because I don't want to waste a whole lot of money making a good one. Uh, Rockland campus is built on granite, and so to have a really good seismograph, you need to have the seismic station or the equipment there that's shown in the insert box, a couple 100 feet below the surface. And that would be super expensive and totally not worth it on our campus. So what we have it is it's basically sitting out towards the parking lot. We could all go out as a class, jump up and down, and make a kid quake. Okay, and it works on this principle of inertia. Okay, and a body in motion stays in motion, a body in rest stays at rest. And what you do is you have that very heavy weight where the pen is attached and it's on a cable. And then you bolt that down and you've got that little roll of paper there. And so when the earth shakes, the paper shakes, but the pen itself stays stationary. And I put that movie that I often show, the little animation, so that you can see. And if you do, are you able to see the animation? Put your finger where that weight is. It's right above the pen. The pen is attached to the weight. It doesn't move. Okay, when the earthquake wave moves through, everything else moves, and it's because of that cable. Okay. So make sure you see that animation. Now, I have seismograms, and this is a seismogram, and the time is pretty important. Time is passing as you move from left to right. And what you do is you have the first wave, which is the fastest wave, the wave that leaves the earthquake site. They all actually leave at the same time, but the one that travels the fastest will arrive at the seismic station first, and that's the P wave. Okay, then the next fastest wave, or the next slowest wave, I guess we would say, is the S wave. Okay, and so you can see where it arrives. All right, and then the surface waves are even slower than the S wave, and they arrive last. And yeah, they are pretty high amplitude. This, I remember the last earthquake I was in. It was the Paso Robles earthquake, and it was, I think, early 2000 something. And when the P wave arrived at my house up in San Ynez, California, it felt like somebody kicked the back of my chair. And I kind of looked around and go, huh? Okay, and then, it was quiet, so you can see how the wave dies out. Okay, and then things started to rattle a little bit. When the first P wave arrived. I'm like, oh, gee, I wonder if we're having an earthquake. And then when the surface waves come, you're like, oh my gosh, we're having an earthquake. And your cabinet doors are flip-flopping, things are shaking. I have a pond outside, and there were waves on the pond, and the fish were flopping around and stuff. I had to fish a few of them off the lawn and put them back in the pond. Got a little exciting. Okay, so that's kind of how it feels. Now, we got to talk about the first two types of waves, those two fastest waves, and they're called body waves. And they're called body waves because they travel through the body of the earth. I use the analogy of sonograms. If your friend says, hey, will you come with me to get a sonogram? And you're like, ooh, no, I don't want to see blood and gore. You don't see blood and gore. They don't cut the mom open to look at the baby. They just pass sound waves through the mom's stomach and, look at the baby through that way. And the baby isn't, messed up or bloodied or anything by it. And every time we have a big earthquake, it does pass waves through the inside of the earth and gives us a great picture, much like a sonogram. And these are those type of waves, so they pass through. So P waves, we talked about that before. That's the fastest wave, the one that felt like a kick to the back of my chair. And they're P for primary. Okay, S wave was the one where, oh, gee, there's some shaking. I wonder if there's an earthquake, that wave. Those are called secondary waves. And sometimes we refer to them as shear waves because that's the way they move. Now, both of these waves move out from the focus. And I know I have a slide coming up on focus, and this is pretty important that you understand this. Make sure you look at this in your book. That is the place, usually beneath the Earth's surface, where the fault broke. Okay, remember the epicenter is the place directly above it. And so the focus has three dimensions, latitude, longitude, and depth. The epicenter has two dimensions, latitude and longitude. Okay, so both of these waves move out from the focus, and they move out in three dimensions or in all directions. So they move up, right, left, out, down in all directions. All right, P waves, we call them compressional waves. They move like a slinky. Okay, if you grabbed one end of a stiff metal slinky, I grabbed the other, and then we just kind of pushed waves at each other, not, swinging it up and down, just pushing. We would push compressional waves at one another. Now, this is a really good way to move through rocks. It's very, how do you say it, efficient. And so these are the fastest. Don't worry about the speed, you guys, but these move the fastest. And these are the ones that will arrive at the seismic station first. It's a push-pull. Think about a slinky, push-pull or compression. And so sound waves move much the same way. Now, sound waves are compressional waves. They pass through gas. I'm talking right now, and my sound waves are going through the atmosphere. Okay, they also pass through liquid, and they pass through solids. And this is important because these will give us a really complete picture of the inside of the Earth, because remember the outer liquid core? Oh yeah. Okay, that's going to be a problem when we get to the S wave. All right, so slinky at rest, think about it. You just push it a little bit and you see the wave, and it's a push-pull or a compression wave, or a expand-dilate wave. Okay, so, and it only moves in one direction. The slinky will bring the wave back at you, but it just moves out from the focus. All right, now, kind of interesting, you guys. I live in cow country now. I've always lived in cow country. After an earthquake, you got to be real careful, because here's a barbed wire fence. I got barbed wire fences all around my property because there's cows next door. There's cows on my property. And what happens is, if you have an earthquake, be very careful. See the part where it snapped? It was stretched so far that it snapped. Now, see the part where it's loose? Okay, that's not a problem. But the very first rung on the left, that's a problem. Never go up to that. You guys know that sometimes guitar strings break? Guitar strings don't take off your head. This could take off your head. What I do is I get a pole, like a PVC pipe, that's longer than the length of that barbed wire, and I push that T-bar back together, and sometimes it snaps, but I keep my head. So be very careful. Also, when you're in cow country after an earthquake, cows get out, and cow versus car is not pretty. Plus, if it doesn't kill you, you still have to pay for the cow. So, injustice of it all, right? But just be a little aware of this. Okay, so these are moving very efficiently, and they're going to arrive at the seismic station first. All right, S waves, secondary waves. Their motion is a shear motion, an up and down motion. They travel slower. Now, I call this Swedish massage hands. Have you guys ever seen someone getting a massage where somebody just is chopping at their back? It kind of looks like that, but it's moving from the epicenter outwards, again, in 3 dimensions. But you know what? You can't shear liquid, so we're going to lose this wave at the outer liquid core. Now, of our 2 body waves, these are more damaging, okay, because of the shearing motion. But don't, worry, is that the surface waves are worst of all because they're slow. And I use a rope or a what is that called? A hose to show this. You reach down and you give it a whip, and you've got a sine wave. It's a sine wave, and it's an up and down motion. Now that wave is going from left to right, but it's using a lot of energy going up and down, and so that's why it's slower. It's not super efficient like my compressional wave. All right, you cannot shear liquid, you cannot shear gas. These pass beautifully through solids, but boy, as soon as they go inside the Earth and they hit that outer liquid core, they just stop. They're dampered. Okay. All right, the surface waves. These are the slowest, and these are the most damaging of all. Now, you guys have bad analogies, I know, but let me tell you. When you're a little kid, you got a big Band-Aid, and your mom's just like, let me just rip it off real fast. And you're like, no, no. And so you run off, and you pull at that Band-Aid, and it pulls, hair by hair or skin, and you do it really slow, and you just make it such a worse thing. So the slower it goes, the more painful it is. Now, as an adult, I have a Band-Aid on that I want to get off. I just do it real fast. Okay, and the waves that travel real slow tend to be the most damaging, just kind of like the pulling off the Band-Aid the slowest. Now, surface waves are different. They are not body waves. They travel at the surface only, and they travel out from the epicenter, not from the focus. Now, they travel in 2 dimensions because they are not going through the body of the Earth. This is very much like if you drop a rock in a pond and you watch the little rings move out. Okay, and that's exactly how it will move out. And let's say you see a huge, surface waves coming right at you, but there's a lake in between you and that earthquake. Okay, guess what? They damper, they're gone, and you don't get shaken by those surface waves. So, always keep a lake between you and a bad fault zone. How's that? So again, they're slower, and so they cause more property damage. Remember, that was the last wave that arrived at my seismic station, and I told you that as soon as those come in, you know you're having an earthquake. You really are rocking and rolling and shaking around. All right, so I do have a slide here. Let's talk. They used to call the focus the hypocenter, but the focus is that place within the Earth where the earthquake began along the fault. Okay, the epicenter is that point on the Earth's surface directly above it. So latitude and longitude, no depth. And you have experience now, you guys. You determine the epicenter of an earthquake using that difference in arrival time at several different seismic stations, the difference in arrival time between P and S waves. We know how fast they move, and so when they arrive at different, times to us, we can figure out where they started from. All right, here's a fault, you guys. I hope you can recognize what type of fault this is. Hanging wall block drops. This is a normal fault. And actually, when you have vertical faults like this, you end up with that fault scarp there. And there's still, fault scarps visible from that 1906 earthquake, the San Francisco earthquake. All right, the earthquake started at the focus. That's where the body waves move out from. But see that the point directly above it on the Earth, that's the epicenter. So that's just the latitude and longitude. And when you have a big earthquake, pretty soon they announce that on the television or on the news or something and tell you where the epicenter was. And it's just a latitude and longitude. The focus is latitude, longitude, and depth. All right, now you guys, you should be experts at this. You need to have 3 different stations because all you can tell is how far away an earthquake occurred. You can't tell what direction. So if I had a good seismic station at school and I said, oh, the earthquake occurred 1,000 miles away, I could get out a compass, a drawing, the ones you draw circles with, and I would put the needle at Rockland, on the Sierra campus, and I would pull the distance to represent 1,000 miles on my map, and I'd make a big circle. And I'd just say, hey, that earthquake happened on that circle. And so you need to have 3 of those, and the 3 circles should intersect at one point, and that will show you your epicenter. Now, here are 2 different seismic stations, and they're feeling the same earthquake. Now, look at the seismogram. The first one is the closer one. 2 reasons. They are on the same time frame. You can see that they're lined up, and the P wave arrived there before it arrived at seismic station B. Okay, the second thing is the difference in arrival time. When the P wave first arrives, where the S wave first arrives is shorter because the left to right axis is time. You can see it labeled. Okay, and then look, on the seismic station B, not only does the P wave arrive later, but the difference in time between when the P wave first arrived and when the S wave first arrived is greater. Okay, so that's pretty cool. All right, here's some real data. 3 different seismic stations feeling the same earthquake. And the last one on the bottom is farthest away, and you can see where they've labeled where the first S wave arrives, the first P wave arrives. You take that on the time scale. Again, the seismogram has the time scale, and then I'll show you guys where they got the number, or how far away it was. Okay, this is where they got the number. See the red curve and the blue curve. This is the seismic travel curves. And unfortunately, we know about these for a bad reason. Nuclear bomb testing. Okay, during World War II, when we were doing the nuclear bomb testing, we knew exactly when we set these things off. And so we were able to see how those waves moved. And so we figured out these curves. And so all you do is you say, okay, if the earthquake was, if there was 4 minutes between when the P wave first arrived and the S wave first arrived, you take that 4 minutes and it's going to fall around, what, 3,000 kilometers from the epicenter. And so you can see that the farther from the epicenter you are, the greater the difference in the arrival time. Now they're curves because these guys actually travel faster the farther they go. They're traveling through the body of the Earth, and the farther they go, they're going through more dense rock. So that's why they're curves. All right, and they're labeled L is a surface wave. Surface waves travel along the surface, and basically we're pretty much assuming that the surface material is what's it called? Constant density. Okay, so hopefully you got a chance to work this out, and if you're in lab, you also got a chance to work this out. It's pretty cool. Again, we got it for a bad reason, but unfortunately, war and greed and the economy and stuff like that sometimes drive some of our discoveries in science. All right, so you get the data from the first seismic station and you draw a circle. Okay, you get the data from the second seismic station, you figure out how far away the earthquake occurred, and you draw a circle. The two circles intersect at 2 points. Okay, we know it's either the top point or the bottom point, but it's not until you bring in the third seismic station to figure out how far they occurred, or the earthquake occurred, that the 3 circles intersect at 1 point, and you have just figured out what the epicenter was. Okay, and you guys see this, the D is the diameter, that is the distance from the quake, and because we don't have any directionality, that's the circle. All right, and again, a lot of these earthquakes do center on Los Angeles. We built our 2 biggest cities in the absolute worst places. San Francisco is right on a bad bend of the San Andreas Fault also. All right, we talked before about earthquakes happen at all plate boundaries, and more than 95% of them are on plate boundaries. But yeah, we have some that are not on plate boundaries. You know why there's earthquakes at Hawaii. It's because of magma movement. Same reason why there's earthquakes at Yellowstone and down near Mammoth Mountain. And so we do know why we get the other percentage. And remember, those hot spots also help support plate tectonics. So this is not anything bad here. And the Pacific Ring of Fire, you guys have been hearing a lot about this lately. It is abnormally active. Okay, I am a little concerned. We should all be prepared. There are earthquake kits. You should have it. Now, I'm a camper, so I have a lot of that. But I'm actually asking myself, should I go out and buy a generator? Because I am on electric, and if the electricity goes out, my well, I'm on a well, it doesn't work. Okay, no more pump, and so I might have to do that. Now I'm lucky I have a pond, so I could filter the water with my backpacking stuff or something like that, or boil it a lot. But this is stuff we need to think about. Okay, and we do get a lot of earthquakes on that mid-ocean ridge system, but those are shallow and pretty weak. All right, now here's earthquake data, and this is 5 magnitude or above, and so you might say, wow, the mid-ocean ridges aren't really showing up. Okay, the mid-ocean ridges have a ton of earthquakes, but they're actually pretty small. It's where plates slide by each other and where plates crash together that we get our biggest earthquakes. So remember, all you'd have to do is connect the dots, and you'd pretty much have all your plate boundaries. You can see Hawaii, guys. Hawaii is very active. It's very active right now, and so that's magma movement. Okay, that's what causes those earthquakes.